Hello guys, trust you're doing fantastic. In today's video, we're going to be looking at more examples of 2's complement form. Alright, so let's go straight into today's business. Now the example says, represent minus 28 in 8-bit 2's complement form. Now this looks a bit complex, but now it's very easy. Now look at it. Now this question is trying to make it a bit complex because this problem is very easy. Now it says 8 bits. So it means that you need to go beyond the minimum number of bits that is required to represent minus 28. This is what it means. Now what this means that if the minimum number of bits required to represent 28 is 5. So what they want you to do is you need to increase the bit to 8. So bear this in mind. That is what they want you to do. They don't want you to just write the minimum bit required to represent minus 28. So let's go straight into solving this question. Now the solution is this. Now remember, using the direct method to convert decimal numbers into binary. For we to represent 28 in binary number system, it means the number of bits, the minimum number of bits required is 1, 2, 3, 4, 5 is 5 bits. In that case, we're going to have the highest value to be 2 raised to the power 4. Then we have 2 raised to the power 3, 2 raised to the power 2, 2 raised to the power 1, and 2 raised to the power 0. Now 2 raised to the power 4 is going to give us 16. That of 3 is going to give us 8. That of 2 is going to give us 4. That of 1 is going to give us 2. And then that of 0 is going to give us 1. So in this case, since we know this direct method, now have it in mind that the minimum bit required to represent 28 in binary is 5. You need to know this. Now if you're wondering and you're saying that how is it 5? Now this is it. Now to represent 28, if you consider 16, you consider 8, and you consider 4. Now if you sum these together, you're going to get 28. And then you have 0, 0. So it means what you need is just 5 bits. So you're going to have 1, 1, 1, 0, 0. So this, in that case, you're going to get 28. So this is how easy it is. Now since the question says we should represent minus 28 in 8 bits, then we need to add extra 2 bits, knowing well that the sign bit for minus has 1 bit. Now if we put all the bits together, we will arrive at 8 bits. This is the simple logic. So you have 5 as the minimum number of bits required to represent 28. Now you have 1 bit which will represent minus, right? You have 1 bit which will represent minus. So that's 6. Then you need to add extra 2 more bits, which will give you 8 bits. That's what it means. Now the extra 2 more bits you need to add is nothing but zeros. So we're going to do padding, 0 padding. We're going to pad with 0, okay, from the left hand side. So that is what we're going to do. So this is pretty very easy, very easy. Alright, so remember this syntax. It's a sign bit and then you have 2's complement actual binary. So this is the same formula we're going to use all through this class. Now, having said that, the actual binary for 28 is equal to 11100. So in this case, we need to do 0 padding. The 2 zeros added before the 1 is nothing but 0 padding. That is why I have to indicate that with a different color of ink. This is the extra 2 bits we have added, which is nothing but zeros to pad, because these bits are not significant. So it means they are not significant. So the significant bit is 1, starting from 1. And then you have 1, 1, 0, 0. So the 2 zeros are not significant. It's just a pad because the question says we need to represent it in 8 bits. So if you count all the bits together, you have 1, 2, 3, 4, 5, 6, 7. So you have 7 bits, and then the last bit, which will make it 8 bits, is the bit coming from the sign. All right, so put everything together, you're going to have 8 bits. So this is how logical the question is, and you have to answer logically. All right, so we know that the sign bit for minus is 1. So since we know this, the actual binary for 28 is this. We paired with the first 2 zeros, and then the actual binary is the 11100, like I explained initially. Now let's go over to the 1's complement for 28. Now for we to achieve or obtain the 1's complement for 28, it means we need to take the inverse of this value. So it means that what you have here is now regarded as the magnitude bit. So it means we need to take the inverse of the magnitude bit. So taking the complement of 28 is going to be, so the complement of 0, 0 is going to be 1, 1. Complement of 1 is going to be 0. Complement of 1, 1 is going to be 0, 0. Complement of 0, 0 is going to be 1, 1. Now, the 1's complement for minus 28 is going to be 1, 1, 1, 0, 0, 0, 1, 1. So now you're wondering, where is this one coming from? This is the bit for the sign, which is representing minus. So that's why we have it here. Very straightforward. Now for we to obtain the 2's complement for minus 28, it means we need to add 1 to the 1's complement. So that's why we have this 1, 1, 1, 1, 1, 0, 0, 0, 1, 1. So plus 1. Now let's proceed with the addition process. Now in binary, 1 plus 1 will give us, it will give us 0 carry 1. So we're going to have a carry. So 1 plus 1 is going to be 0 carry 1. So we put the 1 at this point. So it's going to be 1 plus 1 is going to be 0, and we'll have a carry of 1. We're going to put that 1 at this point. So we're going to have 0 plus this 1. We're going to have 1. Then we have 0, we bring the 0 down, we bring this 0 down, we bring this 1 down, we bring 1 down, and then we bring the final 1 down. So in that case, therefore, the 2's complement for minus 28 in 8 bits will be equal to 1, 1, 1, 0, 0, 1, 0, 0. So this is how simple and easy this question is. Now let's take another example of 2's complement form. Now this example says, what is the equivalent of 2's complement representation of 1101? This is very easy. Now this is the solution. Now follow this simple step to solve this. It's very easy. Now you have this representation form. All you need to do is to write it out. 1100. Sorry, 1101. Now the next thing we need to do, we need to demarcate it. We need to separate it. We need to divide this value into the sign bit and the magnitude bit. Now the first bit you have, it's nothing but the sign bit. That you have this demarcation. So this is to demarcate so that we can have the appropriate syntax. So the first bit is nothing but the sign bit. And then the other bit that you have is nothing but the actual binary, which is also known as the magnitude bit. So we have the magnitude bit to be 1, 0, 1. And then we have the sign bit to be 1. So in this case, we all know that minus, the sign bit for minus is 1. And the sign bit for plus is 0. So in that case, we know that 1 is going to represent minus in this case. So the sign bit for 1 is going to be minus. So the next thing we need to do at this point Now let's obtain the 1's complement form. Now the 1's complement form is going to be taking the inverse. Alright, so we're going to be taking the inverse of this value. We're taking the inverse of the magnitude bit or the actual binary. So this is what we're going to do. So now we know that 1 is minus, so we're going to change that immediately. So we're going to say this one becomes minus. Alright, so let's take the inverse of this. So the inverse of 1 is going to be 0, the inverse of 0 is going to be 1, and the inverse of 1 is going to be 0. So this is nothing but the complement. Now the next step is to obtain the 2's complement form. Now in order for you to obtain the 2 complement form, you need to add 1 to the 1's complement that we have just obtained. So in that case, we're going to have minus 0, 1, 0 plus 1. So if you do this math, 0 plus 1 is 1. Then you bring down this 1, you bring down the 0, and then you bring down the minus sign. This is pretty very easy and straightforward. Now, what we need to do next is to represent this value in decimal. So that is what we want to do. We want to find the equivalent in decimal. So in order for we to do that, we need to go back to the direct method using the direct method. Now, since we have 3 bits, now don't forget this is a sign bit. For the actual binary, we have 3 bits. So it means the highest value we're going to have is going to be 2 raised to the power 2. So we have 2 raised to the power 2, 2 raised to the power 1, and 2 raised to the power 0, so that we can have 3 bits. So it means that where we have 0, it means 4 is absent. The middle value, which is the second value, is 1. It means 2 is present. The last value is 1, which means 1 is present. Now, if you sum it together, you have 2 plus 1, which is 3. So it means that this representation is nothing but minus 3. So the equivalent is equals to minus 3. This is how easy and straightforward it is.